Okay, so here's our next result about pullbacks, and it says that if we have this commuting triangle and these two commuting squares, if we have this commuting triangle and we have these two pullbacks here, then there's going to exist this unique purple arrow which makes this diagram commute. So basically, this commuting triangle here appears on the right hand side, and this middle commuting square up here forms the kind of back of this prism as we're looking at it, the base, if we're assuming we're looking from above. And then this orange pullback here forms this kind of lower wall here as we're looking at it. Now the claim then is that given that information, so given this sort of lower wall in the base, there exists this unique U here which makes this top part SU HQ a pullback square as well, and also makes the whole diagram commute. Okay, so the proof is actually quite short. It's basically that NHQ so we've got N here, so this is NHQ, so here's N going from D to B, and then H from C to D, and then Q from E to C. So if we go along Q, and then H, and then N, that's equal to MQ. So how can we get this result? Well, NHQ is going to equal MQ because NH equals M from this triangle. And then MQ from this middle pullback square equals FP. So NHQ equals FP. Now we think of this as a candidate, as forming the arrows of a candidate for being a pullback of this right orange pullback square. So there's this object E, which is actually from here, but anyway, here it is. And it has these arrows HQ and P, and now we know FP equals NHQ. So that means there has to exist this unique U, which is going to be such that SU equals HQ and RU equals P. Well, RU equals P makes this right-hand triangle commute. SU equals HQ makes this upper kind of wall of our triangular prism commute. And then it follows that the base, well, don't we actually already have that the base commutes, don't we? Because there's only 3 sides to this, and we already know everything has to commute. So the whole diagram commutes, and the other part of the claim is that this square here with sort of perimeter HQ and SU is a pullback. So how can we see this? Well, just imagine snipping off N and P and sort of flattening out this prism. And then if you want, you can turn it all 90 degrees counterclockwise, and you'll basically see it looks just like the pullback lemma. So we have this right rectangle, this right square as a pullback. And we know that the entire sorry, what I'm saying is imagine snipping off P and M. Then we know that this right square is a pullback. And we also have that the base is a pullback. So, in the previous language, the outer rectangle is a pullback. So the pullback lemma tells us that this left square is also a pullback. So that's all we need to know, actually. We know that E is also, not only is E forming a pullback for the base square, or the outer rectangle if you like, it's also, we have that this corner UQ here is also forming a pullback for this top part, which would become the left of the pullback if it was rotated 90 degrees counterclockwise. So basically it's by application of the last result that we're able to prove this.